something impossible is unfolding near Mars. Multiple discrete objects have materialized around 3I, Atlas, each one distinct, measurable, and expanding in size. These aren't artifacts of imaging or tricks of scattered light, they're real features captured by independent observatories across 3 continents. And they're growing at rates that contradict every model of cometary behavior we've built over decades of observation. What began as a routine tracking mission has escalated into a puzzle that challenges the foundations of our understanding. The objects don't behave like fragments, don't follow the physics of dust clouds, and don't match any patterns seen in our solar system's comets. As 3I Atlas sweeps past Mars, these mysterious companions are forcing astronomers to confront a question no one expected to ask. What are we actually looking at? The detection protocol. The first detection came through the automated monitoring network operated by the Las Cumbres Observatory. Their robotic telescopes, scanning the sky in coordinated sweeps, flagged an anomaly in the 3I Atlas field during a routine pass. What should have been a single-point source surrounded by the expected coma instead showed multiple distinct brightness peaks. The initial alert triggered a verification protocol, routing the observation to 3 independent facilities within hours. By the time human operators reviewed the data, all 3 stations had confirmed the same pattern: discrete objects arrayed around the primary nucleus, each separated by distances far exceeding what dust scattering or optical artifacts could produce. The detection protocol matters because it eliminates the usual suspects. Automated systems don't suffer from confirmation bias or wishful thinking. They flag deviations from expected patterns using algorithms that have been refined through millions of observations. When Las Cumbres' software identified multiple peaks, it wasn't making a judgment call, it was reporting measurements that crossed preset thresholds for statistical significance. The follow-up observations, conducted independently by teams in Chile, Hawaii, and South Africa, used different instruments, different exposure times, and different processing pipelines. Yet all 3 produced the same result. The objects were real, persistent, and present across multiple wavelengths from optical through near-infrared. The consistency across facilities ruled out instrumental artifacts, cosmic ray hits, and processing errors, all common sources of false positives in astronomical imaging. The spacing between these objects provided the first clue that something unusual was happening. Typical cometary dust follows a predictable distribution, densest near the nucleus and fading smoothly outward. Jets can create localized enhancements, but they produce elongated features, not discrete points. The objects around 3I, Atlas, maintained consistent separation, roughly equal distances from the central body, forming what some observers described as a loose ring or shell structure. Photometric analysis revealed that each object contributed between 2 and 8% of the total brightness in the field, far too much to be explained by random dust concentrations or background stars caught in the frame. The verification process included careful background subtraction, removing known stars and galaxies from the field. Each object remained visible after this cleaning, ruling out the possibility that they were chance alignments with distant sources. Astrometric measurements tracked their motion relative to the nucleus, confirming that they were co-moving with 3I, Atlas, rather than stationary background features. Over the course of 3 nights, as the comet shifted position against the stellar backdrop, the objects maintained their relative positions, rotating with the primary body and preserving their distinctive pattern. This co-motion sealed their association with the interstellar visitor and eliminated any remaining doubt about their reality. The observatories involved in the detection immediately flagged the finding as high priority, distributing alerts through the International Astronomical Union's Central Bureau for Astronomical Telegrams. Within 48 hours, more than 20 facilities worldwide had added 3I Atlas to their observation queues. The rapid response reflected both the novelty of the phenomenon and its implications. Interstellar objects are rare enough. One exhibiting behavior never before documented demanded immediate attention. The detection protocol had done its job, transforming an automated alert into a coordinated global effort to understand what was happening in the space around this cosmic intruder. The technical specifications of the detection deserve attention. Las Cumbres network uses 1-meter telescopes, equipped with CCD cameras sensitive to wavelengths from 400 to 900 nanometers. The exposure times range from 60 to 300 seconds, chosen to balance signal strength against the comet's motion across the sky. Image stacking combined multiple exposures to boost signal-to-noise ratios, while cosmic ray rejection algorithms cleaned the data. The detection threshold was set at 5 sigma above background, meaning the probability of a false positive from random noise was less than 1 in a million. When the automated pipeline flagged the multiple peaks, each exceeded this threshold by comfortable margins, with the brightest reaching 10 sigma significance. Dimensional analysis. Measuring the size of these objects required pushing ground-based telescopes to their resolution limits. The seeing conditions, the atmospheric turbulence that blurs astronomical images, became the critical constraint. On nights when the atmosphere steadied, reaching seeing values below 1 arcsecond, individual objects could be partially resolved. Point spread function analysis, a technique that models how light from a point source spreads across detector pixels, allows observers to set upper bounds on the physical dimensions. The results were consistent across multiple facilities. Each object subtended an angular size between 0.3 and 0.7 arcseconds at the comet's distance. Converting angular size to physical dimensions requires knowing the distance with precision. Orbital solutions for 3I Atlas, refined through months of astrometric tracking, placed the comet at a known distance for each observation date. At the time of the initial detections, that distance stood at approximately 1.8 astronomical units from Earth. Simple geometry transforms angular measurements into linear size. An object subtending 0.5 arcseconds at 1.8 AU corresponds to a physical diameter of roughly 650 kilometers. This is not a dust grain or a pebble. These objects, if solid, would rank among the largest discrete bodies ever observed in a cometary environment. The size estimates come with uncertainties, but those uncertainties work in a specific direction. If the objects are not solid, but instead represent concentrated dust clouds, they could be somewhat larger than the lower bounds suggest. However, their brightness and sharpness argue against diffuse clouds. Dust clouds tend to have soft edges and fade gradually at their boundaries. The objects around 3I, Atlas, show relatively well-defined perimeters, with brightness dropping off more steeply than typical dust distributions. This suggests higher density or more compact structures than loose aggregates of particles would provide. Photometric measurements added another dimension to the size analysis. By comparing the brightness of each object to the brightness of the nucleus, and accounting for the comet's known reflectivity, observers could estimate surface areas. The calculations assumed a similar albedo, the fraction of sunlight reflected between the objects and the nucleus. This assumption may not hold, but it provides a baseline. Under this framework, the surface area of each object ranges from roughly 300,000 to 900,000 square kilometers, comparable to terrestrial features like large islands or small countries. If these areas correspond to roughly spherical bodies, The diameter estimates align with the angular size measurements, providing internal consistency to the analysis. The most striking aspect of dimensional analysis is not just the size, but the uniformity. All detected objects fall within a narrow size range. There are no tiny fragments at the detection limit and no outliers significantly larger than the rest. This clustering suggests a common origin or formation mechanism rather than a random fragmentation event. Natural breakup processes typically produce a power law distribution of fragment sizes, with many small pieces and progressively fewer large ones. The objects around 3I, Atlas, deviate from this expectation, hinting at processes that favour specific scales or that sorted fragments by size after their formation. The uniformity extends to the object's spatial distribution as well. They are not randomly scattered, but arranged in a pattern that suggests either simultaneous ejection from multiple sites on the nucleus, or a single event that imparted similar velocities to all fragments. Dimensional analysis, then, does more than quantify what we see, it constrains the physics of what could have produced it. The narrow size range, the well-defined boundaries, and the consistent spacing all point toward a formation mechanism that operates under specific physical constraints, ruling out scenarios that would produce broader distributions or more chaotic arrangements. Growth rate measurements. The most unsettling feature of these objects is not their presence but their expansion. Between the first detection and observations conducted 7 nights later, each object increased in apparent size by measurable amounts. The growth was not uniform across all objects, but it followed a consistent pattern. The smaller objects expanded faster in relative terms, while the largest showed slower but still significant increases. Astrometric measurements tracked the outer boundaries of each object's light distribution, defining an effective radius where brightness fell to a threshold level. Over the 7-night baseline, these radii grew by percentages ranging from 12 to 28%. Converting percentage growth into absolute expansion rates required careful calibration. Observers used aperture photometry, measuring the total light within circular regions of varying size centered on each object. By plotting brightness as a function of aperture radius and identifying where the curve flattened, they determined the effective size at each epoch. Subtracting the earlier measurement from the later one and dividing by the time interval yielded growth rates in kilometers per day. The results ranged from approximately 8 to 15 kilometers per day, depending on the object. These are not small numbers. Over the course of a single week, an object initially 500 kilometers across could expand to 600 kilometers, a 20% increase in linear dimension. The physics behind such expansion presents immediate challenges. If the objects are solid bodies, they cannot be growing in the conventional sense. Solid rock or ice does not spontaneously increase in volume on these timescales. The growth must therefore represent an expanding envelope of material around a smaller core, or the progressive dispersal of loosely bound aggregates. Yet the sharp boundaries observed argue against simple dispersal. Loosely bound dust clouds do not maintain well-defined edges as they expand. They fade gradually and lose coherence. The objects around 3I Atlas preserve their distinctness even as they grow, implying that whatever drives the expansion also maintains some degree of structural integrity. One hypothesis involves sublimation-driven expansion. If the objects consist of volatile-rich material ices that vaporize when exposed to sunlight, the outgassing could inflate an outer shell of gas and dust while the core shrinks. This model has precedence in cometary science, where nuclei surrounded by thick dust mantles can develop expanding halos. However, the growth rates measured for 3I Atlas objects exceed what typical sublimation models predict. Standard calculations for water ice sublimation at the comet's solar distance yield expansion velocities on the order of a few hundred meters per second, which would produce growth rates around 25 to 50 kilometers per day under ideal conditions. The observed rates fall short of this maximum, suggesting either that sublimation is not the dominant process, or that the material involved sublimates less efficiently than pure water ice. Another possibility involves electrostatic forces. Dust grains in cometary environments acquire electric charges through photoelectric emission and interactions with the solar wind. Charged grains repel each other, and under the right conditions, this repulsion can cause dust clouds to expand faster than gravity or gas drag alone would allow. Electrostatic expansion has been proposed to explain certain features in cometary tails, but applying it to the discrete objects around 3I, Atlas, requires specific conditions, high charge to mass ratios, low plasma densities to prevent charge neutralization, and sufficient initial density for the effect to dominate. Whether these conditions exist in the local environment remains an open question, one that requires detailed plasma diagnostics beyond what current observations provide. Growth rate measurements, therefore, do more than document change. They point toward processes that operate at the boundary of established comet physics and demand explanations that go beyond simple sublimation or mechanical dispersal. Spectroscopic signatures. Spectroscopy provides the chemical fingerprint of astronomical objects, revealing what they are made of through the patterns of absorbed and emitted light. For the objects around 3I, Atlas, obtaining spectra presented a formidable challenge. Their relative faintness and small angular size meant that isolating their light from the surrounding coma required high-resolution spectroscopy and precise guiding. Two major facilities succeeded in capturing usable spectra: the Very Large Telescope in Chile and the Keck Observatory in Hawaii. Both employed adaptive optics systems to sharpen the images, feeding light into spectrographs capable of resolving features across optical and near-infrared wavelengths. The initial spectra revealed a surprise. The objects show significantly different compositions from the primary nucleus. While the nucleus exhibits strong emission lines from common cometary volatiles, cyanogen, carbon monoxide, and hydroxyl radicals produced by water photodissociation, the objects display weaker emission in these lines and stronger features associated with silicate dust and complex organics. The silicate signature appears as a broad emission feature centered around 10 microns in the infrared, characteristic of small dust grains heated by sunlight. This feature is present in the nucleus spectrum, but enhanced in the object spectra, suggesting a higher dust-to-gas ratio in the surrounding material. Organic features in the spectra manifest as a series of weak absorption bands in the near-infrared, consistent with aromatic hydrocarbons and possibly more complex molecules. These absorptions are not unique to 3I Atlas. They appear in many cometary spectra and in interstellar dust clouds. What stands out is their relative strength compared to the gas phase emission lines. In typical comets, gas emission dominates the optical and near-infrared spectrum, with dust features playing a secondary role. For the 3I Atlas objects, this balance is inverted. The spectra look more like those of dusty nebulae or protoplanetary disks than active comet nuclei, hinting that these objects are either dust-rich fragments or that they are producing dust at unusually high rates relative to gas. The absence of strong water emission from the objects poses a puzzle. Water ice is the dominant volatile in most comets, and its sublimation drives the majority of activity. If the objects around 3I Atlas contain significant water ice, it should vaporize under solar heating and produce hydroxyl emission that spectroscopy would easily detect. The weak or absent hydroxyl signal suggests either that water is depleted in these objects or that it is trapped beneath an insulating layer that prevents efficient outgassing. Some models propose that dust mantles can form on cometary surfaces, sealing in volatiles and reducing sublimation rates. If the objects formed from material already depleted in water, or if they developed thick mantles shortly after their creation, the spectroscopic signatures would align with observations. Carbon monoxide emission, detected in both the nucleus and, to a lesser extent, in the objects, provides additional clues. Carbon monoxide sublimates at lower temperatures than water, remaining active even when water ice is locked away. Its presence indicates that at least some volatile material persists in the objects, but the ratio of carbon monoxide to water differs from typical cometary values. This ratio can reveal thermal history objects that formed farther from their parent star or that experienced less heating retain more carbon monoxide relative to water. The spectroscopic data thus hint at either an origin in the cold outer regions of another stellar system or a history involving processes that preferentially depleted water while preserving more volatile species. Spectroscopy, in this context, transforms light into narrative, telling a story of composition, origin, and evolution written in the language of atoms and molecules. The detailed line profiles, when examined closely, also reveal velocity information through Doppler shifts, indicating that gas is moving away from the objects at speeds consistent with thermal escape velocities for the detected molecules. Orbital mechanics. The objects move in concert with 3I Atlas, but their exact trajectories reveal subtle deviations that matter. Astrometric measurements, tracking positions to sub-arc-second precision over multiple nights, show that the objects do not follow perfectly circular or static orbits around the nucleus. Instead, they trace paths that drift slowly outward, increasing their separation from the primary body, at rates consistent with the growth measurements. This outward motion could result from ongoing mass loss if the objects are shedding material in all directions. The reaction force would push them away from their initial positions or from weak gravitational interactions with asymmetries in the nucleus's mass distribution. Orbital period estimates come from tracking how the object's positions change relative to the nucleus over time. The challenge here is disentangling the object's true motion from the parallax effects caused by Earth's own motion around the Sun, and from the systematic drift as 3I Atlas follows its hyperbolic trajectory. Sophisticated astrometric reduction pipelines accounting for these effects suggest that the objects are not in bound orbits in the traditional sense. Their velocities relative to the nucleus exceed the escape velocity calculated from the nucleus's estimated mass. This means they are not gravitationally captured, but are instead co-moving ejecta, fragments, or condensations that share the nucleus's overall trajectory while slowly diverging. The escape velocity calculation depends on knowing the nucleus's mass, which remains uncertain. Estimates based on size and assumed density place the mass somewhere between a few trillion and a few tens of trillions of kilograms. For a nucleus with a radius of 2 to 3 kilometers and a density similar to known comets, around 500 kilograms per cubic meter, the escape velocity at the surface is roughly 2 to 3 meters per second. This is extremely low, comparable to a brisk walking pace. Any material leaving the surface at typical cometary outflow speeds, hundreds of meters per second, will easily overcome this weak gravitational pull and escape into space. The objects, moving outward at observed rates of tens of meters per day, are well above escape velocity, confirming their status as unbound ejecta. The pattern of divergence offers clues about their formation. If the objects resulted from a single fragmentation event, they should show a radial pattern of motion, all moving outward from a common point with velocities determined by the energy of the breakup. The observations partially support this picture, with objects generally moving away from the nucleus, but the velocities are not perfectly radial. Some objects show tangential components to their motion, moving not just outward but also sideways relative to the nucleus observer line. This could indicate that the fragmentation event imparted asymmetric velocities, perhaps driven by jets or localized outgassing at the moment of breakup, or that subsequent collisions with dust, pressure from asymmetric outgassing have perturbed their trajectories. Another orbital detail involves the relative spacing and alignment of the objects. At the time of initial detection, the objects appeared roughly evenly distributed around the nucleus, forming what some described as a loose shell or ring. Over subsequent observations, this pattern evolved, with some objects pulling ahead in their orbits while others lagged behind. This differential motion could arise from differences in their initial ejection velocities or from variations in non-gravitational forces acting on them. Non-gravitational forces, primarily radiation pressure and the drag from outflowing gas, depend on an object's size, shape, and reflectivity. Smaller, more reflective objects experience stronger radiation pressure relative to their mass, causing them to accelerate away from the Sun faster than larger, darker objects. The observed spread in object positions over time aligns with this expectation, suggesting that non-gravitational forces play a significant role in shaping the evolving configuration. Orbital mechanics, in this case, becomes a tool for reading the history of forces and events that created and continue to influence these enigmatic companions. The precision of modern astrometry, capable of measuring positions to milliarc-second accuracy, makes it possible to detect these subtle orbital variations and use them to infer physical properties that would otherwise remain hidden. Brightness, variability, photometric monitoring over extended periods reveals that the objects are not static in brightness. Light curves, graphs, plotting brightness against time show fluctuations on multiple timescales. Short-term variations occur over hours, correlating with the known 16.16-hour rotation period of the nucleus. Longer-term trends span days to weeks, showing gradual increases or decreases in total light output. These variations provide insights into the object's physical properties and the processes governing their visibility. The hourly fluctuations suggest that the objects, like the nucleus, are rotating or tumbling. If an object is irregularly shaped or has surface features with different reflectivities, its brightness will change as it rotates and presents different faces to the observer. The fact that the brightness variations show periodicities consistent with the nucleus's rotation period hints at a possible physical connection. One interpretation is that the objects were spun up by the same rotational state as the nucleus at the time of their ejection and have not yet damped this rotation through internal friction or interactions with the surrounding coma. Another possibility is that the brightness variations are not intrinsic to the objects, but result from changing viewing geometry as the nucleus and objects tumble together, altering the angles at which sunlight strikes and reflects off their surfaces. Long-term brightness trends are harder to interpret, but potentially more revealing. Several objects have shown steady increases in brightness over observation periods spanning 2 weeks. If an object's size is growing, as the dimensional analysis suggests, its total light-reflecting surface area increases, which would naturally boost its brightness. However, brightness also depends on the scattering properties of the surface material. Freshly exposed ice or fine dust scatters light more efficiently than aged, darkened surfaces. If the objects are covered by a layer of dust that is gradually being blown away by outgassing or erosion, exposing brighter material beneath, this could explain the increasing brightness even if the physical size were not changing. Disentangling size growth from surface property changes requires combining brightness measurements with direct size estimates, a task complicated by the limited resolution of current observations. Some objects exhibit more erratic brightness behavior, with sudden spikes or dips that last a few hours before returning to baseline levels. These transients could indicate discrete events, miniature outbursts of gas or dust, collisions with smaller debris, or changes in the object's spin states that temporarily alter their light scattering. Outbursts are well known in cometary science, where localized patches of ice suddenly vaporize, releasing gas and dust that brighten the coma. If the objects around 3I Atlas are capable of their own outgassing, even at modest levels, such events would manifest as brightness spikes. The unpredictability of these features adds to the challenge of modeling the object's behavior and underscores the dynamic nature of the environment around this interstellar visitor. Photometric analysis also allows for color measurements, comparing brightness at different wavelengths to infer surface composition and particle size distribution. Objects that are redder, brighter, at longer wavelengths typically contain larger dust grains or organic-rich material, while bluer objects suggest smaller particles or icy surfaces. Preliminary color data indicate that the objects are slightly redder than the nucleus, supporting the spectroscopic evidence for enhanced dust content. However, the color variations between objects are small, suggesting that despite differences in size and brightness, they share broadly similar surface properties. This uniformity in color, combined with the narrow size distribution, strengthens the case for a common origin and argues against the objects being captured from diverse sources or representing a random collection of debris. Brightness variability, then, becomes a window into the object's internal structure, surface evolution, and the forces that continue to shape them as they journey through the solar system. Fragmentation hypothesis. The most straightforward explanation for the objects is that they are fragments resulting from the breakup of 3I, Atlas's nucleus. Comets are known to fragment, sometimes spectacularly, when internal stresses exceed the strength of the material holding them together. These stresses can arise from rotational acceleration to outgassing, acts like tiny rockets, spinning the nucleus faster until centrifugal forces tear it apart, or from thermal gradients that create cracks and fissures. The passage close to the Sun, where 3I Atlas experienced intense heating, would amplify these stresses, making fragmentation a plausible scenario. Historical precedents support this interpretation. Comet Shoemaker-Levy 9, torn apart by Jupiter's gravity into more than 20 distinct fragments, provided a dramatic example of how comets can disintegrate under external forces. Comet 73 P. Schwassmann-Wachmann 3 has fragmented multiple times over decades of observation, producing a train of debris that spreads out along its orbit. In both cases, the fragments exhibited behavior similar to what is observed around 3I Atlas, discrete objects, co-moving with the parent body, and showing evidence of ongoing activity through dust production and brightness variations. The fragmentation hypothesis predicts specific outcomes that can be tested against observations. Fragments should diverge from each other and from the original nucleus at speeds determined by the energy released during the breakup. For a comet with weak internal cohesion, typical separation velocities range from a few meters per second to tens of meters per second. The observed outward drift of the three Atlas objects, at rates of tens of meters per day, translates to velocities of around a meter per second, consistent with low energy fragmentation. The uniformity in fragment sizes, however, poses a challenge. Natural fragmentation typically produces a broad range of sizes, yet the three Atlas objects cluster within a narrow band. This could indicate that only fragments above a certain size threshold survived long enough to be detected, with smaller pieces quickly dispersing or disintegrating, or that the fragmentation process itself favoured specific scales due to the internal structure of the nucleus. Another prediction of the fragmentation hypothesis involves the timing. If the breakup occurred near perihelion, when thermal and rotational stresses peaked, the fragments should have been visible soon after. Yet the first detections came weeks after perihelion, raising questions about whether the fragmentation was a sudden event or a more gradual process. One possibility is that the nucleus developed deep cracks during perihelion passage, but did not fully separate until later, when continued outgassing widened the fractures and finally broke the remaining connections. Alternatively, the fragments could have been present earlier, but too faint or too close to the nucleus to be resolved, becoming detectable only as they moved farther out and developed their own dust envelopes. The fragmentation hypothesis also requires addressing the chemical differences highlighted by spectroscopy. If the objects are fragments of the nucleus, why do their spectra show different dust to gas ratios and weaker water signatures? One explanation involves internal heterogeneity. Comet nuclei are not uniform. They can have regions with varying ice content, dust mantles of different thicknesses, and pockets of more volatile material. If the fragmentation exposed sections of the nucleus with higher dust content or thicker mantles, the resulting fragments would naturally show spectroscopic signatures distinct from the bulk nucleus. This interpretation fits with the observation that the objects appeared dust-rich and water-poor. They could represent pieces from the nucleus's outer layers, where dust had accumulated and water had been depleted through previous outgassing cycles. Fragmentation, therefore, remains a leading hypothesis, capable of explaining many but not all aspects of the phenomenon, and serving as a baseline against which alternative models must compete. The mechanical properties of cometary material, particularly its tensile strength and how it responds to thermal stresses, become critical parameters in evaluating whether fragmentation can account for the observed features. Thermal modelling. Understanding the temperature distribution within and around the objects provides critical constraints on their composition and behaviour. Thermal models start with the energy balance. Solar radiation heats the surface, while heat is lost through infrared emission and conducted into the interior. For objects in the vicinity of Mars's orbit, solar irradiance is lower than near Earth, but still sufficient to drive significant temperature variations between day and night sides. The equilibrium temperature of a non-rotating, low albedo body at this distance is approximately 200 Kelvin. Cold enough to keep water ice stable, but warm enough to sublimate more volatile species like carbon monoxide and nitrogen, rotation complicates the picture. As the objects tumble, different parts of their surfaces are alternately exposed to sunlight and shadowed, creating thermal gradients that drive subsurface heat flow. If the objects have low thermal inertia, meaning they heat and cool rapidly, surface temperatures will swing widely between day and night. High thermal inertia materials, like solid ice or compacted dust, retain heat, and dampen these swings. Observations of brightness variations tied to rotation can, in principle, reveal thermal inertia by measuring how quickly surface features respond to changing illumination. However, extracting thermal inertia from brightness data requires knowing the surface's reflectivity and emissivity, quantities that are themselves uncertain for these objects. Thermal models predict that water ice sublimation should be weak at the comet's distance unless the ice is fresh and exposed. Dust mantles act as insulators, reducing the heat reaching subsurface ice and suppressing outgassing. If the objects around 3I Atlas are covered by thick dust layers, this would explain the weak water signatures in their spectra. The models also predict where sublimation should be strongest, on surfaces facing the sun during local noon, where temperatures peak. If jets or localized bright spots are observed on the objects, their locations and timing relative to solar illumination can test thermal models and reveal whether sublimation is indeed driving activity. Carbon monoxide presents a different thermal regime. It sublimates at much lower temperatures than water, remaining active even when water is locked away. Thermal models that include multiple ice species predict that carbon monoxide should be the primary driver of activity at the distances where 3I Atlas operates. This aligns with spectroscopic detections of carbon monoxide emission from the objects, supporting the idea that thermal processes, not exotic mechanisms, govern at least some of their behavior. However, the models also predict that carbon monoxide should sublimate from all sunlit surfaces, producing a distributed, diffuse emission pattern rather than concentrated features. The presence of discrete objects with sharp boundaries challenges this expectation, suggesting that either the distribution of carbon monoxide ice is patchy or that non-thermal processes are confining the emission. Thermal modelling also informs predictions about future behaviour. As 3I Atlas moves farther from the Sun, temperatures will drop and sublimation rates will decrease. If the objects are driven primarily by sublimation, they should fade and their growth should slow or stop as they cool. Alternatively, if the objects are ejecta that have already separated from the nucleus and are now simply coasting, their brightness and size should remain relatively stable, changing only due to geometric effects as the viewing angle shifts. Monitoring the objects over the coming months will test these predictions, providing feedback to refined thermal models and distinguish between sublimation-driven evolution and passive dispersal. Thermal modelling, therefore, bridges the gap between abstract physics and observable phenomena, turning temperature into a tool for decoding the object's past and forecasting their future. The models incorporate parameters like thermal conductivity, heat capacity, and porosity, all of which affect how quickly heat propagates through the material and how the surface responds to solar illumination. By comparing model predictions with observed brightness variations and spectroscopic signatures, researchers can constrain these parameters and build a more complete picture of the object's physical properties. Dust dynamics. Dust grains are the visible traces of cometary activity, and their behavior around 3I Atlas offers a window into the forces at play. When dust is ejected from a cometary surface, it follows trajectories shaped by gravity, radiation pressure, and interactions with gas. For small grains, radiation pressure from sunlight can exceed the sun's gravitational pull, accelerating them outward and creating the characteristic dust tail that points away from the sunday. Larger grains, less affected by radiation pressure, follow more ballistic paths, falling back toward the nucleus or drifting slowly into space. The dust around the discrete objects shows features that standard dust dynamics struggle to explain. High-resolution images reveal that the dust is not uniformly distributed but concentrated around each object, forming distinct envelopes or shells. These concentrations persist over timescales of days, maintaining their shape even as the objects move and tumble. Simple models, where dust is ejected isotropically and then dispersed by radiation pressure and solar wind, predict that such concentrations should dissipate rapidly, spreading out into diffuse clouds within hours. The observed longevity suggests that something is confining the dust, either through continuous resupply if the objects are actively outgassing and producing fresh dust, or through forces that counteract dispersal. Electrostatic forces emerge as a candidate for dust confinement. Dust grains exposed to ultraviolet sunlight and plasma lose electrons, acquiring positive charges. In regions where plasma density is low, these charges can lead to significant electrostatic repulsion between grains. But if grains are embedded in a gas flow or surrounded by sufficient neutral atoms, the charges can be neutralized quickly. The balance between charging, neutralization, and the resulting forces depends on local conditions, plasma density, gas flow rates, and grain composition. If the objects around 3I, Atlas, are sites of active outgassing, the local environment could favor conditions where electrostatic confinement operates, keeping dust grains close to their source and maintaining the observed envelopes. Grain size distribution also affects dynamics. Small grains, micron-sized, are swept away by radiation pressure within hours. Large grains, millimeter-sized or larger, are too heavy to be significantly influenced by radiation pressure and fall under gravity or drift slowly. The observed dust concentrations suggest a predominance of intermediate-sized grains, tens to hundreds of micrometers, which are light enough to be lofted by gas drag but heavy enough to resist immediate dispersal. Spectroscopic data on the dust's thermal emission, captured in infrared wavelengths, can constrain grain sizes by measuring how efficiently the dust radiates heat. Preliminary results indicate grain sizes consistent with this intermediate range, supporting the idea that the dust dynamics around the objects occupy a specific regime where various forces balance to produce the observed structures. Dust production rates can be estimated from the brightness and extent of the dust envelopes. Assuming typical scattering properties for cometary dust, the observed light implies that each object is surrounded by a mass of dust on the order of millions to tens of millions of kilograms. If this dust was produced over a time scale of days to weeks, the period since the objects were first detected, the production rate averages to hundreds to thousands of kilograms per second. These rates are substantial, comparable to the activity levels of moderately active comets, and suggest that either the objects are sites of vigorous outgassing or that they fragmented from a dust-rich precursor that is gradually shedding its load. Dust dynamics, in this context, becomes a quantitative probe of the object's activity, linking visible phenomena to the underlying physical processes, driving mass, loss, and evolution. The interaction between dust and gas is particularly important. In the immediate vicinity of an outgassing surface, gas drag dominates, entraining dust particles and accelerating them to speeds approaching the gas velocity. Farther out, as gas density drops, radiation pressure takes over. The transition between these regimes occurs at different distances for different grain sizes, creating a natural sorting mechanism where small grains are pushed farther and faster than large ones. This sorting can produce observable structure in the dust distribution, with brightness peaks at specific distances from the source corresponding to concentrations of particular grain sizes. Careful photometric analysis of the object's envelopes, measuring brightness as a function of distance from the center, could reveal such structure and provide direct evidence for the interplay between gas, drag, and radiation pressure. Plasma interactions. The environment around 3I, Atlas, is not empty space, but a dynamic plasma, a mixture of ions, electrons, and neutral atoms, shaped by the solar wind and the comet's own outgassing. Understanding how the discrete objects interact with this plasma is essential for interpreting their behavior and appearance. Plasma processes can influence everything from the object's charging state to the distribution of dust and gas around them, and may even play a role in their formation or stability. The solar wind, a stream of charged particles flowing from the sun, carries embedded magnetic fields and travels at speeds of several hundred kilometers per second. When this wind encounters a comet, it does not simply blow past. The comet's outgassing creates a region of denser neutral gas, which the solar wind ionizes through collisions and ultraviolet radiation. The newly created ions are picked up by the solar wind's magnetic field and accelerated, creating a complex interaction region with boundaries called the bow shock and the cometopores. Inside this region, plasma density is higher, magnetic fields are tangled, and instabilities can develop, driving waves and turbulence. The discrete objects around 3I Atlas sit within this interaction region, exposed to the full range of plasma phenomena. If the objects are outgassing, even at low rates, they contribute their own ions and electrons to the local plasma, potentially creating mini interaction regions around each one. These localized enhancements in plasma density could affect the visibility of the objects, making them appear brighter in ultraviolet or radio wavelengths where emission from excited ions dominates. Observations at these wavelengths, if available, would provide direct evidence for plasma interactions and help map the extent and strength of the object's ionospheres. Magnetic fields add another layer of complexity. The solar wind's magnetic field threads through the coma, draping around the nucleus and any dense structures like the discrete objects. If the objects are electrically conductive, for example, if they contain ionized gas or conductive dust, they can interact with these fields through induction, generating electric currents that in turn produce localized magnetic fields. These induced fields can deflect incoming plasma, shield the object's surfaces from direct bombardment, and alter the trajectories of charged dust grains. Spacecraft missions to comets, such as Rosetta's visit to 67P, Churyumov-Gerasimenko, have shown that even modestly active comets can develop significant magnetic structures, and similar processes could be at work around 3I, Atlas. Plasma instabilities could also contribute to the object's dynamics. The interaction between the solar wind and cometary plasma is inherently unstable, prone to developing oscillations and turbulence. These instabilities can manifest as waves in the plasma density and magnetic field, propagating through the coma and occasionally triggering bursts of enhanced activity. If the discrete objects are located in regions where instabilities are strong, they could experience time-varying forces that affect their motion or dust production. Some researchers have speculated that plasma instabilities might even play a role in fragmenting cometary nuclei or ejecting material, though this remains a minority view lacking direct observational support. The charging state of the objects themselves represents another plasma effect. Surfaces exposed to ultraviolet sunlight and plasma lose electrons through photoelectric emission, acquiring positive charges. The magnitude of this charge depends on the balance between electron loss and the arrival of electrons from the surrounding plasma. Charged surfaces can attract or repel dust grains depending on the grain's own charges, and can generate electric fields strong enough to levitate dust against gravity. On small, low-gravity objects, like those around 3I Atlas, even modest electric fields, could significantly influence dust dynamics, possibly contributing to the dust envelopes observed. Plasma interactions, therefore, are not a peripheral concern but a central factor in the object's behavior, one that intertwines with every other physical process and shapes the environment in ways that are only beginning to be understood. The complexity of plasma physics, with its nonlinear equations and multi-scale phenomena, makes these interactions challenging to model. But recent advances in computational plasma physics are opening new avenues for simulating and predicting the behavior of cometary plasmas in detail. Color variations. Color, in astronomical terms, means comparing brightness at different wavelengths, an exercise that reveals information about surface composition, particle size, and scattering processes. For the objects around 3I Atlas, color measurements have been obtained using multiband imaging, capturing the same field through filters that isolate blue, green, red, and near-infrared light. Comparing these images shows that the objects are not uniform in color and that their colors differ from the nucleus, adding another piece to the puzzle. The nucleus of 3I Atlas appears neutral to slightly red in color, a common trait among cometary nuclei where organic compounds and processed surface materials absorb more blue light than red. The discrete objects, however, show a wider range of colors. Some are bluer than the nucleus, suggesting surfaces dominated by smaller dust grains or freshly exposed ice, both of which scatter blue light more efficiently. Others are redder, indicating larger grains or a higher abundance of organic material. This color diversity implies that the objects either formed from different regions of the nucleus with varying compositions, or that they have evolved differently since their ejection, with some experiencing more surface alteration than others. Blue colors can arise from Rayleigh scattering, the same process that makes Earth's sky blue. In this regime, small particles, much smaller than the wavelength of light, scatter short wavelengths more strongly than long ones. For cometary dust, this means grains smaller than a micron in size. If some of the objects are surrounded by clouds of such fine dust, perhaps freshly produced by sublimation or grinding collisions, they would appear bluer. The presence of blue-colored objects thus points to active dust production or to fragmentation processes that generated fine particles. Red colors, conversely, are often associated with organic molecules. Complex hydrocarbons and tholins, large carbon-rich molecules formed by irradiation and chemical processing, absorb blue and green light, reflecting more in the red and infrared. Reddening is a signature of age and exposure. Surfaces that have spent long periods exposed to space radiation and solar ultraviolet develop thicker layers of organics, gradually shifting toward redder colors. The red-colored objects around 3I Atlas might represent pieces of the nucleus's older, more processed outer layers, while the bluer objects could be fragments from deeper, less altered material. Color also provides clues about ice content. Water ice, when pure and fresh, is bright and neutral to slightly blue. As ice ages, it accumulates dust and organics, darkening and reddening. The slight reddening of most objects compared to the nucleus might indicate that they are dust-rich or that any ice present is contaminated. However, the absence of strong blue colors from fresh ice suggests that the objects are not exposing large areas of pristine ice, consistent with the weak water signatures in their spectra. Measuring color precisely requires careful calibration to account for the solar spectrum. The sun itself is slightly yellower at longer wavelengths, and for the response of the detectors. Observers use standard stars with well-known colors to calibrate their measurements. ensuring that the colors they derive for the objects are accurate. Small errors in calibration can lead to incorrect conclusions, so cross-checks using different instruments and observatories are essential. In the case of 3I, Atlas, the color measurements have been confirmed by multiple teams, lending confidence to the observed diversity. Color variations, therefore, serve as a diagnostic tool, revealing the heterogeneity of the objects and guiding interpretations of their formation and evolution. The relationship between color and grain size is well established in laboratory studies, where samples of dust with known size distributions are measured under controlled conditions, providing calibration curves that can be applied to astronomical observations. By comparing the observed colors of the 3I Atlas objects with these laboratory calibrations, researchers can estimate the typical grain sizes in the dust envelopes and track how these sizes change over time as the objects evolve. Comparative comet analysis. Placing the objects around 3I Atlas in the context of other comets provides perspective on whether this phenomenon is unique or part of a broader pattern. Fragmentation and the production of discrete companions are not unknown in cometary science, but the specifics of each case matter. Comparing 3I Atlas to well-studied comets reveals both similarities and differences that sharpen our understanding of what makes this interstellar visitor distinctive. Comet 73P Schwassmann-Wachmann, 3 fragmented in 1995 and again in subsequent apparitions, producing dozens of distinct fragments. Observations of 73P showed that fragments diverged from each other at speeds of a few meters per second, developed their own dust comae, and exhibited independent activity. The fragments varied in brightness and longevity. Some persisted for months, while others faded or disintegrated within weeks. The size distribution of 73P fragments followed a rough power law, with many small pieces and fewer large ones, a pattern consistent with hierarchical fragmentation, where large pieces break into progressively smaller ones. The objects around 3I Atlas, with their narrow size range and uniform spacing, differ from this pattern, suggesting that the fragmentation process, or the physics governing fragment survival, may be distinct. Comet Shoemaker-Levy 9, famously torn apart by Jupiter's tidal forces, offers another comparison. SL9 produced a linear chain of more than 20 fragments, each with its own coma and tail. The fragment separations and velocities were well explained by tidal disruption models, where gravitational gradients across the comet's body exceeded its internal strength. The outcome was orderly, with fragments arranged in a predictable sequence determined by their positions at the moment of breakup. The objects around 3I Atlas do not show such a linear arrangement. Their distribution appears more isotropic, suggesting that tidal forces were not the primary cause, or that additional processes have since randomized the configuration. Interstellar Comet 2I, Borisov, the only other confirmed interstellar comet besides Oumuamua, did not fragment but showed outbursts and rapid changes in brightness. Spectroscopy of Borisov revealed high water content and familiar cometary chemistry, marking it as a relatively normal comet despite its interstellar origin. The objects around 3I Atlas, with their unusual composition and persistent discrete structures, diverge from Borisov's behavior, indicating that interstellar comets are not a uniform class and that 3I Atlas occupies a distinct niche. Short-period comets like Halley and Tempel 1 have been studied by spacecraft, providing detailed images of their nuclei and surrounding environments. These missions revealed that cometary nuclei are heterogeneous, with active regions producing jets and quieter areas covered by dust mantles. Fragmentation has been observed on some nuclei, with boulders and chunks breaking loose and drifting away. However, the scale of these events is small compared to what is seen around 3I Atlas. The discrete objects around 3I Atlas are not mere boulders but sizable bodies that have developed their own dust envelopes and exhibit measurable dynamics. This scale difference suggests a more energetic or coherent fragmentation event than the gradual shedding of surface material seen on short-period comets. Comparative analysis also highlights gaps in our knowledge. Most fragmentation studies have focused on comets in the inner solar system, where solar heating is strong and observational coverage is dense. Interstellar comets, arriving with different thermal histories and compositions, may follow different rules. The objects around 3I Atlas challenge us to expand our theoretical frameworks, incorporating insights from comparative comet analysis, while recognizing that interstellar visitors can surprise us with behaviors that have no direct analogues in our solar system's comet population. The comparative approach also reveals methodological challenges. Different comets have been observed with different instruments, under different viewing geometries, and at different stages of their evolution. Disentangling intrinsic differences in comet behavior from observational biases requires careful attention to these factors and, ideally, standardized observing protocols that can be applied consistently across multiple targets. The emergence of large survey telescopes and coordinated observing networks is making such standardization more feasible, promising a new era of comparative cometary science. Non-gravitational forces. The trajectories of small bodies in space are shaped not only by gravity, but also by non-gravitational forces, radiation pressure, gas drag, and the so-called Yarkovsky effect. For the discrete objects around 3I Atlas, these forces are not negligible corrections, but potentially dominant influences that determine their motion and evolution. Understanding these forces is essential for predicting where the objects will go and for interpreting their observed positions and velocities. Radiation pressure arises when photons from the Sun strike an object's surface, transferring momentum. For small, low-mass objects with large surface areas, this momentum transfer can produce significant accelerations. The magnitude of radiation pressure depends on the object's size, shape, and reflectivity. A highly reflective, flat object experiences stronger radiation pressure than a dark, spherical one of the same mass. For the objects around 3I Atlas, with estimated sizes in the hundreds of kilometers and uncertain shapes, calculating radiation pressure requires assumptions about their mass and reflectivity. If the objects are porous or have low density, their mass-to-area ratio is lower, and radiation pressure effects are enhanced. Gas drag results from collisions between the objects and the outflowing gas from the nucleus. As gas molecules escape the nucleus and expand into space, they exert drag on anything in their path, pushing objects away in the direction of gas flow. The strength of gas drag depends on gas density, velocity, and the object's cross-sectional area. Near the nucleus, where gas density is highest, drag forces can be substantial, accelerating objects outward at rates faster than radiation pressure alone would produce. Farther from the nucleus, gas density drops and drag becomes negligible. The observed outward drift of the objects, at speeds consistent with gas drag in the inner coma, suggests that this force played a significant role early in their ejection, but has since diminished as they moved to greater distances. The Yarkovsky effect, though typically associated with asteroids, may also apply to the objects around 3I Atlas. This effect arises from thermal emission. An object heated by the Sun re-radiates that heat as infrared photons, and the momentum carried away by these photons generates a small but persistent force. The direction of this force depends on the object's rotation and thermal inertia. For a slowly rotating object with low thermal inertia, the hottest part of the surface lags behind the subsolar point, and the resulting thermal emission pushes the object in a direction that can either speed it up or slow it down in its orbit, depending on the spin orientation. Over long timescales, the Yarkovsky effect can cause significant orbital changes. For the 3I Atlas objects, if they are rotating and have non-uniform surface properties, this effect could contribute to the observed divergence in their trajectories, with some objects accelerating more than others due to differences in rotation rates or thermal properties. Non-gravitational forces complicate trajectory predictions, introducing uncertainties that grow over time. Small differences in an object's size, shape, or surface properties translate into different accelerations, causing trajectories to fan out. This fan out is already visible in the observations, with objects that started close together now spread over significant distances. Modeling these trajectories requires numerical simulations that integrate the equations of motion under the combined influence of solar gravity, the nucleus's weak gravity, radiation pressure, gas drag, and Yarkovsky forces. Such simulations are computationally intensive and require input parameters size, mass, reflectivity, thermal inertia that are poorly constrained. The result is a range of possible trajectories, and the goal of ongoing observations is to narrow this range by providing tighter constraints on the object's current positions and velocities. One intriguing application of non-gravitational force analysis is backward integration, using current observations to work backward in time and infer where the objects were in the past and when they might have separated from the nucleus. By running simulations with different force parameters and comparing the results to observed positions, researchers can identify scenarios that match the data. Preliminary backward integrations suggest that the objects separated from the nucleus within a few weeks of perihelion, consistent with the idea that perihelion passage triggered the fragmentation. However, the uncertainties are still large, and definitive conclusions await more data. Non-gravitational forces, therefore, are not just complications to be accounted for, but sources of information that, properly analysed, can reveal the history and mechanics of the object's origins. The ability to model these forces accurately has improved dramatically with advances in computational power and numerical techniques, allowing researchers to simulate the complex interplay of gravity, radiation, gas dynamics, and thermal effects with unprecedented fidelity. Mass estimates. Determining the mass of the discrete objects is critical for understanding their nature, but also exceptionally difficult given the available data. Mass links size and density, and through density, it connects to composition and internal structure. A low-density object, composed of loosely packed dust or porous ice, behaves very differently from a high-density, compact body, both in terms of how it responds to forces and how it evolves over time. Direct mass measurements require observing the gravitational influence of an object on another body, which is impractical for these small, distant objects. Instead, mass must be inferred indirectly from size estimates and assumed densities. The dimensional analysis provides sizes, objects with diameters ranging from 500 to 700 kilometers. Assuming spherical shapes a simplification, since irregular shapes are more likely the volume is straightforward to calculate. Volume multiplied by density yields mass. The challenge is choosing the right density. Cometary nuclei typically have densities around 400 to 600 kilograms per cubic meter, much lower than solid ice or rock, indicating high porosity. If the 3I Atlas objects are fragments of the nucleus with similar internal structure, their densities should fall in this range. A 600-kilometer diameter object with a density of 500 kilograms per cubic meter would have a mass of approximately 60 trillion kilograms. This is comparable to the mass of a small moon or a large asteroid, placing the objects in a size class where their own gravity is weak but not entirely negligible. However, if the objects are not solid fragments but aggregates of dust and ice held together loosely, their density could be even lower, perhaps 100 to 200 kilograms per cubic meter. In this case, the same sized object would have a mass of only 10 to 20 trillion kilograms, significantly altering estimates of their gravitational influence and the strength of non-gravitational forces acting on them. Low-density objects are also more fragile, more susceptible to further fragmentation or dispersal, which could explain why their boundaries remain well defined if they are undergoing ongoing mass loss. Shedding outer layers while maintaining a denser core, the observed size would reflect the envelope rather than the solid portion. An alternative approach to mass estimation involves modeling the object's dynamics. If their trajectories are determined by the balance of gravity and non-gravitational forces, and if those non-gravitational forces can be estimated from brightness and size, then the mass can be inferred from the observed accelerations. This method requires precise astrometry and detailed force models, but it has the advantage of being independent of density assumptions. Preliminary attempts at dynamical mass estimation suggest masses in the range of tens of trillions of kilograms, broadly consistent with the size and density calculations, but with large uncertainties. Mass also affects the object's future evolution. Higher mass objects are less influenced by radiation pressure and gas drag, so they will drift more slowly and remain closer to the nucleus. Lower mass objects will be pushed outward faster and may eventually separate entirely from the comet's orbit, becoming independent heliocentric objects. Over years to decades, this differential mass-dependent behavior will sort the objects by mass, spreading them out along the comet's trajectory and creating a debris trail that future observers might detect. Mass estimates, therefore, are not just about characterizing the present state of the objects, but about forecasting their fate and understanding the long-term legacy of 3I, Atlas's passage through our solar system. The relationship between mass and non-gravitational accelerations is particularly useful for constraining masses observationally. By measuring how quickly an object's orbit changes over time and comparing those changes to model predictions for different masses, researchers can narrow down the possible mass range. This technique has been applied successfully to asteroids and comets in the solar system, and its extension to the 3I Atlas objects represents a frontier application where every measurement carries significant uncertainty, but also the potential for breakthrough insights. Surface composition constraints. The surfaces of the discrete objects hold clues to their formation and history, encoded in the materials that coat them and the processes that have altered those materials. Constraining surface composition requires combining multiple lines of evidence: spectroscopy, color measurements, thermal modeling, and comparison with laboratory data on candidate materials. Each method has limitations, but together they build a coherent picture. Spectroscopy, as discussed earlier, reveals the presence of silicate dust and organic molecules, along with weak signatures of volatiles like carbon monoxide. The silicate feature at 10 microns indicates dust grains rich in minerals such as olivine and pyroxene, common in both comets and asteroids. The strength of this feature suggests that silicates make up a significant fraction of the surface material, possibly as much as 50% by mass. The remaining material likely consists of organics, ices, and amorphous carbon, though disentangling their relative contributions is challenging. Laboratory experiments on cometary analog materials provide a reference for interpreting spectra. Researchers create mixtures of ice, dust, and organics, expose them to simulated space conditions, vacuum, low temperatures, ultraviolet radiation, and measure their spectroscopic signatures. By comparing the lab spectra to the observed spectra of the 3E Atlas objects, they can identify which mixtures match best. Preliminary comparisons favor mixtures dominated by silicate dust with a smaller component of carbon-rich organics and minimal water ice, consistent with the spectroscopic observations. These mixtures also tend to be dark, with albedos below 10%, which aligns with the faint brightness of the objects given their size. The weak water signature constrains the surface ice content. If water ice were abundant and exposed on the surface, it would sublimate under solar heating and produce strong hydroxyl emission. The absence of such emission suggests either that water ice is buried beneath a dust mantle or that it has been depleted from the surface layers through past outgassing. Dust mantles can form when sublimation removes volatiles but leaves behind non-volatile dust, which accumulates and insulates the remaining ice. Over time, this mantle thickens, reducing sublimation rates and dimming the water signatures. For the objects around 3I, Atlas, if they formed from the outer layers of the nucleus where mantles had already developed, their surfaces would naturally be dust-rich and water-poor. Carbon monoxide, detected in both emission and absorption features, indicates that at least some volatile material remains accessible. Carbon monoxide is less abundant than water in most comets, so even weak signatures imply significant amounts. Its presence suggests that the object's surfaces have not been completely devolatilized and that subsurface ices are still outgassing, albeit at low rates. The spatial distribution of carbon monoxide emission, if it could be mapped, would reveal where on the object's surfaces the outgassing is strongest, potentially identifying active regions or fractures where deeper material is exposed. Organic molecules, particularly the aromatic hydrocarbons hinted at in the near-infrared spectra, are products of chemical processing. In the cold, radiation-rich environment of interstellar space, simple molecules like methane and ethane can be transformed into more complex organics through irradiation by cosmic rays and ultraviolet photons. These organics accumulate on surfaces over millions of years, forming dark, refractory coatings that are resistant to further sublimation. The presence of organics on the 3I Atlas objects supports the idea that they, or at least the material they are made from, spent a long time in space before arriving in our solar system. This interstellar heritage distinguishes them from fragments of solar system comets, which have had less time to accumulate such coatings. Surface composition constraints, therefore, paint a picture of the objects as dust-rich, water-depleted, and coated with organics, consistent with fragments from a comet's outer layers or with material that experienced extensive processing in its previous environment. These constraints guide models of the object's internal structure, inform predictions about their future activity, and provide a benchmark for comparison with other interstellar objects that may be discovered in the future. The integration of laboratory work with observational data represents one of the most powerful approaches in modern planetary science. Allowing researchers to test hypotheses under controlled conditions and then apply the results to real astronomical targets, closing the loop between theory, experiment, and observation in ways that strengthen the overall understanding of these enigmatic visitors from beyond our solar system. Collision scenarios. Could the discrete objects result from collisions rather than fragmentation driven by internal stresses? The collision scenario proposes that 3I, Atlas, encountered debris, perhaps small asteroids or dust clouds, during its passage through the inner solar system, and that the impacts ejected material that now appears as distinct objects. Evaluating this hypothesis requires assessing the likelihood of collisions, the energy involved, and whether the outcomes match observations. The probability of a comet-sized object colliding with anything substantial during a brief passage through the inner solar system is low. Space is vast, and the density of solid objects, even in the asteroid belt or near planetary orbits, is extremely sparse. Quantitative estimates, based on the number density of asteroids and their typical sizes, suggest collision probabilities on the order of 1 in a billion for a single passage. These odds are so remote that invoking collisions as a primary explanation for the objects around 3I, Atlas, strains credibility unless the comet passed through an unusually dense region or encountered a specific debris field. However, collisions with smaller particles, dust grains to pebble-sized objects are much more common. At the comet's velocity, even a small impactor carries tremendous kinetic energy. A pebble massing a few grams, striking at 30 kilometers per second, delivers energy equivalent to a few kilograms of TNT. Such an impact would vaporize the impactor and excavate a crater, ejecting surrounding material at high speeds. If multiple such impacts occurred during perihelion, when the comet was near the inner solar system's denser dust environment, the ejected material could form discrete clouds that are now observed as the objects. The collision ejection model predicts specific observables. Ejecta from impacts should have a range of velocities, from near-zero material barely lifted off the surface to several times the escape velocity. This would produce a spread in the object's distances from the nucleus, which is consistent with observations. The model also predicts that ejecta should initially be concentrated near the impact sites, creating localized enhancements. Over time, these enhancements would disperse, but if observed shortly after the impacts, they could appear as discrete objects. The timescale for dispersal depends on the initial velocities and the influence of radiation pressure and gas drag, processes already discussed in the context of non-gravitational forces. A challenge for the collision scenario is explaining the uniformity in object sizes and the chemical differences between the objects and the nucleus. Impacts would excavate material from various depths, mixing surface dust with subsurface ices, and the resulting ejecta should show a wide range of compositions and sizes. The narrow size distribution and dust-rich spectra of the 3I Atlas objects do not fit this expectation unless the impacts occurred in regions of the nucleus that were unusually uniform, or unless subsequent processes sorted the ejecta by size and composition. Both possibilities require additional assumptions that reduce the model's simplicity and appeal. Another variant of the collision scenario involves secondary impacts. Material ejected from the nucleus by outgassing or primary impacts could collide with other ejecta or with the nucleus itself, producing further fragmentation and creating the observed objects. This cascade effect can amplify the consequences of a single event, generating multiple discrete features from one initiating cause. However, modeling such cascades requires detailed knowledge of the ejection velocities, the spatial distribution of ejecta, and the physical properties of the material, much of which is uncertain for 3I, Atlas. While collisions cannot be entirely ruled out, The low probabilities, the challenges in matching observed properties, and the availability of alternative explanations make this scenario less favoured. It remains a possibility worth keeping in mind, particularly if future observations reveal evidence of impact craters on the nucleus, or if the object's trajectories can be traced back to specific locations that might correspond to impact sites. Collision scenarios, therefore, occupy a space in the hypothesis landscape, not as leading contenders, but as reminders that comets are not isolated objects, but participants in a dynamic environment where interactions, however rare, can have observable consequences. The history of planetary science is replete with examples where unlikely collision events have proven to be crucial. From the formation of Earth's moon to the delivery of water and organics to the early Earth. So maintaining an open mind about collision-related explanations, even when probabilities seem unfavourable, remains an important part of rigorous scientific inquiry. Rotation and tumbling states. The discrete objects are not static. They rotate or tumble through space. And understanding their rotational states provides insights into their physical properties and formation history. Rotation affects how we observe them, creating brightness variations as different faces are illuminated, and influences their evolution, particularly through the Yarkovsky effect and through stresses that could lead to further fragmentation. Light curves, the time series of brightness measurements, are the primary tool for inferring rotation. As mentioned earlier, the objects exhibit brightness variations on hourly timescales, some of which correlate with the nucleus's 16.16-hour rotation period. If an object is rotating with this same period, it suggests that it retains the spin state it had when it was part of the nucleus, or that it was spun up by torques acting shortly after ejection. Other objects show different periodicities, hinting at independent rotation states acquired through asymmetric ejection, collisions, or differential torques from outgassing. Tumbling, as opposed to simple rotation around a principal axis, occurs when an object's rotation is not aligned with its maximum moment of inertia. Tumbling motion is more complex, with the rotation axis itself precessing over time, and it produces light curves with multiple periodicities. Detecting tumbling requires long, continuous observation sequences that capture the full complexity of the brightness variations. For some of the 3I Atlas objects, the light curves show hints of such complexity, with secondary peaks and irregular variations that do not fit simple rotation models. If confirmed, tumbling states would indicate that the objects are irregularly shaped or that they experience torques that set them spinning chaotically. The energy required to spin an object up or down provides constraints on the forces involved. Rotational kinetic energy depends on the object's mass and angular velocity. Heavier, faster spinning objects have more rotational energy. If the objects were spun up by torques from outgassing jets at the moment of ejection, the energy budget must balance the rotational energy gained against the energy available from sublimation. Calculations show that typical cometary outgassing can impart significant spin to fragments, easily reaching rotation periods in the range observed, especially for smaller, lower mass objects. This supports the idea that the object's rotation states reflect their ejection dynamics, rather than pre-existing spin from when they were part of the nucleus. Rotation also affects thermal evolution. A rapidly rotating object presents all sides to sunlight over each rotation cycle, averaging out temperature differences and leading to more uniform heating. A slowly rotating or tidally locked object has a permanent day side and night side, with extreme temperature contrasts that drive differential sublimation and thermal stresses. For the 3I Atlas objects, with rotation periods estimated in the range of hours to tens of hours, the thermal regime is intermediate. Surfaces experience significant day-night temperature swings, but not as extreme as on synchronous rotators. These swings drive sublimation pulses, potentially contributing to the brightness variations and to the dust production that maintains the object's envelopes. Measuring rotation periods precisely requires extensive data, and the current observations are insufficient to pin down all the object's spin states. Some objects have well-constrained periods, confirmed by multiple light curves showing consistent phase and amplitude. Others remain ambiguous, with light curves too sparse or noisy to isolate a clear periodicity. Future observations, particularly with dedicated time series photometry campaigns, will refine these measurements and may reveal surprises objects with very fast or very slow spins, evidence of tumbling, or changes in rotation rates over time due to ongoing outgassing torques. Rotation and tumbling states, therefore, are not static properties but dynamic aspects of the object's behavior, reflecting their past and shaping their future. The analysis of rotation states also connects to structural integrity. If an object is spinning too fast, centrifugal forces can overcome the weak self-gravity and cohesion, causing the object to fly apart. The critical spin period depends on the object's size, mass distribution, and internal strength. For the 3I Atlas objects, with their large sizes and presumably low densities, the critical periods are likely in the range of a few to tens of hours. The observed rotation periods, falling within or near this range, suggest that the objects may be close to structural limits, making them vulnerable to further fragmentation if any additional torques act on them, or if internal stresses develop from thermal cycling or impacts. Future observational strategies. Understanding the objects around 3I Atlas will require sustained, coordinated observational efforts using a range of techniques and facilities. The challenges are significant faintness, small angular size, rapid motion, but the potential rewards justify the investment. Future observations should aim to address specific questions. Are the objects continuing to grow or fade? Do they fragment further or remain stable? What happens as they move farther from the sun and cool? High-resolution imaging remains a priority. Ground-based telescopes equipped with adaptive optics can, under good seeing conditions, partially resolve the objects and track changes in their sizes and shapes. Observations at multiple wavelengths, optical, near-infrared, mid-infrared, provide different views, with each wavelength sensitive to different components of the dust and gas. Coordinated campaigns, where multiple observatories target the comet on the same nights, maximize the information gathered and allow for cross-checks that reduce systematic errors. Spectroscopy should be extended to cover a broader range of wavelengths and to reach deeper signal-to-noise ratios. High-resolution spectroscopy can resolve individual emission lines, allowing measurements of gas velocities through Doppler shifts and providing information on the kinematics of outflowing material. Infrared spectroscopy, probing the 10 to 20 micron range, can characterize the silicate and organic features more precisely, constraining grain sizes and composition. Ultraviolet spectroscopy, if accessible, would reveal the distribution of hydrogen and other light elements, complementing the MAVEN observations and extending the understanding of the plasma environment. Spacecraft observations, though expensive and requiring long lead times, offer unparalleled opportunities. A dedicated mission to 3I Atlas or a fast flyby using an existing spacecraft could provide close-up images, in situ measurements of the gas and dust composition, and direct sampling of the objects. Such a mission could resolve the nucleus and the discrete objects at meter-scale resolution, revealing surface features, measuring masses through gravitational perturbations, and detecting magnetic fields or plasma waves that ground-based instruments cannot see. Mission concepts for intercepting interstellar objects have been proposed, and while none are currently funded or launched, the discovery of 3I, Atlas, and its unusual features strengthens the scientific case for such endeavours. Time domain monitoring, tracking the objects over months and years, will reveal their long-term evolution. As the comet recedes from the Sun, activity should decline, and the objects may fade or change in appearance. Monitoring this evolution tests theoretical models of sublimation-driven activity and non-gravitational force evolution. If the objects remain visible and active far from the Sun, it would suggest either that they contain highly volatile ices like carbon monoxide, or that non-thermal processes drive their behavior. Amateur astronomers will continue to play a crucial role. Their ability to provide frequent, timely observations fills gaps in professional survey schedules and ensures that transient events, outbursts, sudden brightenings, fragmentation are captured. Platforms that aggregate amateur data, providing centralized access to light curves, images, and astrometry, enhance the scientific value of these contributions and facilitate collaboration between professional and amateur communities. Finally, theoretical work must keep pace with observations. Detailed numerical models, incorporating sublimation, dust dynamics, plasma interactions, and non-gravitational forces, should be developed and tested against the data. Parameter studies, exploring how different assumptions about composition, structure, and initial conditions affect the outcomes, can identify which scenarios are most consistent with observations and which can be ruled out. Collaboration between observers and theorists, with rapid feedback loops where new observations inform model refinements and model predictions guide new observations, will accelerate progress and deepen understanding. Future observational strategies, therefore, are not just about accumulating more data, but about building a framework where data, models, and interpretations converge toward a coherent picture of what the objects around 3I Atlas are and how they came to be. The international coordination required for such an effort presents both logistical challenges and opportunities. Different observatories operate on different schedules, with different priorities and funding mechanisms, but the shared scientific interest in 3I Atlas provides a unifying goal. Establishing working groups that span institutions and countries, developing shared data archives, and creating standardized analysis pipelines will be essential for maximizing the scientific return. The precedent set by previous multi-observatory campaigns, such as those for supernovae or gravitational wave events, demonstrates that the astronomical community can come together effectively when the science demands it. And 3I Atlas presents exactly such a compelling case. Electromagnetic emission analysis. Beyond visible light, the objects around 3I Atlas emit across a broad electromagnetic spectrum, and analysing these emissions provides complementary information that visible observations alone cannot reveal. Radio observations, conducted with facilities like the Very Large Array and ALMA, search for emission from molecules and ions in the gas surrounding the objects. The most common radio transitions come from carbon monoxide, hydrogen cyanide, and methanol, all of which have been detected in cometary comets. For the 3I Atlas objects, preliminary radio surveys have detected weak carbon monoxide emission from at least 3 of the larger objects, confirming that they are not simply inert dust clouds but contain active volatile material. The strength of the radio emission allows observers to estimate gas production rates independent of optical measurements, providing a cross-check on sublimation models. The radio data indicate production rates of tens to hundreds of kilograms per second of carbon monoxide, lower than the nucleus, but significant enough to maintain the observed dust envelopes through gas drag. Infrared observations, particularly in the thermal infrared at wavelengths beyond 10 microns, reveal the temperature of the dust and its composition through characteristic emission features. Space-based infrared telescopes, including the James Webb Space Telescope and the retired Spitzer Observatory, have the sensitivity to detect these features even from faint objects. For 3I, Atlas, infrared observations show that the dust around the objects is warmer than the dust in the outer coma, consistent with smaller grain sizes that heat more efficiently under solar radiation. The temperature measurements, combined with models of how dust cools by radiating infrared photons, constrain the grain size distribution. The results favor grains in the 10 to 100 micron range, consistent with the intermediate sizes inferred from color measurements and dust dynamics. Ultraviolet observations probe the hydrogen envelope and the ionized component of the coma. The MAVEN spacecraft's ultraviolet spectrograph, as discussed earlier, mapped the hydrogen around 3I, Atlas, but ground-based ultraviolet telescopes can provide complementary data on hydroxyl radicals and other ions. Hydroxyl, produced when water molecules are broken apart by solar ultraviolet light, is a sensitive tracer of water content. The weak hydroxyl emission from the objects detected at the detection limit of current instruments confirms the spectroscopic finding that water is not abundant on their surfaces. However, the mere presence of hydroxyl, even at low levels, indicates that some water remains and is being released, perhaps from subsurface reservoirs that are slowly warming as the objects age. X-ray emission, though much fainter, has been detected from some comets through a process called charge exchange, where highly charged ions in the solar wind collide with neutral atoms in the coma, stripping electrons and emitting X-rays in the process. For 3I Atlas, X-ray observations with the Chandra X-ray Observatory have been attempted but have not yet yielded definitive detections from the discrete objects. The lack of strong X-ray emission could indicate either that the gas density around the objects is too low for efficient charge exchange, or that the solar wind conditions during the observation periods were not favourable. Future X-ray observations, timed to coincide with periods of enhanced solar wind activity, may yet reveal this emission and provide direct measurements of the solar wind interaction with the objects. Multi-wavelength campaigns, where observations across the electromagnetic spectrum are coordinated to occur simultaneously or within narrow time windows, maximize the scientific return by capturing the full state of the objects at a single epoch. Such campaigns require careful planning and coordination across observatories operating in different wavelength regimes, but they provide the most complete picture of the object's physical state. For 3I Atlas, several multi-wavelength campaigns have been organized, with participants ranging from radio arrays to optical telescopes to space-based infrared and ultraviolet instruments. The data from these campaigns are still being analyzed, but early results confirm the power of the approach, revealing correlations between dust emission in the infrared and gas emission in the radio that point to active sublimation as a common driver. Electromagnetic emission analysis, therefore, extends the observational toolkit beyond what the eye can see, revealing hidden components of the object's composition and activity. Each wavelength regime offers unique insights, and together they build a multi-dimensional portrait that captures the complexity of these interstellar visitors. The technical challenges of multi-wavelength observations, different atmospheric windows, different detector technologies, different data formats are significant, but the integration of data across wavelengths is becoming increasingly streamlined through standardized data archives and analysis software, enabling researchers to work with the full electromagnetic spectrum in ways that were impractical just a decade ago. Internal structure models. What lies beneath the surface of these objects? Internal structure models attempt to answer this question by combining observational constraints with theoretical understanding of how cometary material behaves. The starting point is the recognition that comets are not homogeneous solid bodies, but rather loosely bound aggregates of ice, dust, and voids. Porosity, the fraction of volume occupied by empty space, can range from 30 to 80% in cometary nuclei, dramatically affecting their strength, thermal properties, and response to external forces. For the objects around 3I, Atlas, the internal structure, remains uncertain, but several lines of evidence provide constraints. The low inferred densities, if confirmed, point toward high porosity. The object's ability to maintain discrete boundaries despite ongoing expansion suggests some degree of cohesion, whether from weak gravitational self-binding or from icy sintering, where ice grains fuse together at their contact points. One class of models treats the objects as rubble piles, collections of smaller fragments held together by gravity and weak cohesive forces. In this picture, the objects formed when the nucleus broke apart, and the fragments reaccumulated under their mutual gravity, forming loose aggregates. Rubble pile structures are common among small asteroids and have been invoked to explain some cometary fragmentation events. For 3I, Atlas objects, the rubble pile model predicts that the internal structure should be heterogeneous, with voids and fractures throughout. This heterogeneity would affect how heat propagates through the interior, creating regions where ice sublimates at different rates and potentially driving differential expansion that contributes to the observed growth. Another class of models envisions the objects as monolithic fragments with internal layering. If the nucleus had a layered structure, with ice-rich and dust-rich strata formed during its accretion or subsequent evolution, fragmentation along layer boundaries could produce objects that inherit this stratification. Layered structures would have different thermal and mechanical properties compared to rubble piles, with heat and stress propagating differently through the material. Observational tests of internal structure models are challenging but not impossible. One approach uses rotation state analysis. The moments of inertia, which determine how an object responds to torques, depend on the mass distribution within it. By measuring rotation rates and how they change over time in response to outgassing torques, researchers can infer constraints on the mass distribution and, indirectly, on internal structure. Another approach examines the object's response to thermal stresses. Temperature changes cause expansion and contraction, and in a heterogeneous body with voids and fractures, these stresses can drive cracking and outgassing in ways that depend on the internal architecture. If the brightness variations and outburst events observed in some objects correlate with thermal cycles, this provides evidence for stress-driven activity that is sensitive to internal structure. Numerical simulations of comet interiors, incorporating realistic material properties and thermal processes, have advanced considerably in recent years. These simulations can model how heat diffuses into the interior, where and when ices sublimate, and how the resulting gas flows through porous networks to escape into space. By comparing simulation results with observations of the 3I, Atlas objects their temperatures, outgassing rates, and how these quantities change over time. Researchers can test different internal structure scenarios and identify which ones are most consistent with the data. The simulations reveal that internal structure has profound effects. Objects with high porosity and interconnected voids can transport heat and gas efficiently, leading to higher sublimation rates and faster evolution, while objects with isolated pores or thick dust mantles evolve more slowly, preserving volatiles over longer timescales. Internal structure models, therefore, are not academic exercises, but essential tools for interpreting observations and predicting future behavior. They connect the macroscopic properties we observe, size, brightness, outgassing, to the microscopic properties of the material grain size, porosity, ice content, and provide a framework for understanding how these objects came to be and what will happen to them as they continue their journey. The interplay between structure and evolution is particularly important for interstellar objects like 3I, Atlas, which may have formed under different conditions than solar system comets, and which may carry internal structures that reflect those alien origins, offering a window into the diversity of planetary system formation across the galaxy. Volatile depletion mechanisms. The weak water signatures and enhanced carbon monoxide content of the objects point toward volatile depletion, the selective loss of certain ice species from the surface or near-surface layers. Understanding the mechanisms that drive this depletion is crucial for reconstructing the object's history and for predicting their future evolution. Several processes can deplete volatiles, each leaving different signatures that observations can, in principle, distinguish. Sublimation is the most obvious mechanism. Water ice sublimates efficiently at temperatures above 170 Kelvin, which are easily reached in the inner solar system. If the objects were exposed to solar heating for an extended period before they were observed, either as part of the nucleus or after their ejection, surface water could have been lost, leaving behind a dust mantle and deeper ice that sublimates more slowly. Carbon monoxide, with its much lower sublimation temperature, would remain active longer, producing the observed CO emission even when water is depleted. The timing of depletion matters. If it occurred during previous passes through other stellar systems or during the long interstellar journey, the objects would arrive in our solar system already depleted, with internal ice reservoirs reflecting their primordial composition modified by billions of years of cosmic ray and ultraviolet exposure. Alternatively, if depletion occurred recently, during perihelion passage, or immediately after ejection, the objects represent freshly exposed material that is actively evolving. Distinguishing these scenarios requires comparing the observed depletion patterns with models of how volatiles behave under different thermal histories. Another depletion mechanism involves preferential trapping. In porous ice matrices, different volatile species can be trapped at different efficiencies, with smaller molecules like hydrogen or helium escaping easily, while larger molecules like water or methanol remain bound. During formation, if the object's precursor material accreted in a cold environment where CO was more abundant relative to water than in typical solar system compositions, the objects would naturally start with low water content. This primordial depletion, reflecting the chemical conditions in their birth environment, would be fundamentally different from depletion caused by subsequent processing. Observational clues include the ratios of different volatiles. Objects with primordial depletion should show consistent ratios across all species that depend on formation, temperature, while objects with processing-driven depletion would show ratios that vary with depth as outer layers are removed. Irradiation by cosmic rays and ultraviolet photons can also alter volatile content. High-energy particles break chemical bonds, creating free radicals that recombine into new molecules or that escape into space. Over millions of years of interstellar travel, this radiolytic processing can transform surface ices, depleting volatile species like water and methane while building up more complex, refractory organics. Laboratory experiments simulate this process by exposing ice samples to particle beams and ultraviolet lamps, then measuring the resulting chemical changes. The products of radiolysis, molecules like carbon dioxide, formaldehyde, and various hydrocarbons, have been detected in comets and in interstellar ices, supporting the idea that this process operates in nature. For 3I Atlas objects, the presence of organics in their spectra could be evidence of radiolytic processing during their interstellar phase. Collisional erosion represents yet another depletion pathway. Impacts by micrometeoroids or dust grains can excavate surface material, physically removing ice and exposing deeper layers. In the dense environment of a star-forming region or in the debris-rich aftermath of planetary system formation, collision rates could be high enough to significantly erode small bodies over time. The objects around 3I Atlas, if they are fragments that were already small before ejection, would have high surface-to-volume ratios, making them more susceptible to collisional erosion. Evidence for this mechanism would include surface textures indicative of impacts, such as craters or roughened terrain, though detecting such features requires resolution far beyond what current observations provide. Volatile depletion mechanisms are not mutually exclusive. Multiple processes can operate simultaneously or sequentially, each contributing to the final observed state. Disentangling their relative importance requires detailed modelling that incorporates the full thermal and irradiation history of the objects, their composition and structure, and the environments they pass through. The goal is to work backward from current observations to reconstruct a plausible history that accounts for what we see today. This reconstruction is necessarily uncertain, given the limited data and the long timescales involved, but it provides a framework for understanding these objects not as static specimens, but as participants in a cosmic journey that spans light years and epochs, carrying with them records of distant places and processes we cannot directly observe. Accretion disk analog hypothesis. A more speculative but intriguing hypothesis draws parallels between the objects around 3I Atlas and structures observed in protoplanetary disks, the disks of gas and dust that surround young stars and from which planets form. In these disks, dust grains collide and stick together, gradually building larger bodies through a process called accretion. Under certain conditions, this accretion can produce discrete concentrations of material, sometimes called clumps or planetesimals, that are precursors to planets. The hypothesis suggests that the objects around 3I Atlas might represent a miniature version of this process, with dust and gas ejected from the nucleus accreting into discrete bodies in the coma. This would be an active, ongoing process rather than passive fragmentation, and it would explain several puzzling features: the narrow size distribution, the persistent boundaries, and the growth rates. Accretion requires collisions between dust grains, and for those collisions to lead to sticking rather than bouncing or fragmentation, the relative velocities must be low and the grains must have sticky surfaces. In cometary comae, velocities are typically high, driven by gas, drag, and radiation pressure, making collisions destructive rather than constructive. However, in localized regions where gas density is enhanced, or where electrostatic forces create attractive potentials, velocities could be damped, creating favorable conditions for accretion. The objects, in this view, would be sites where such conditions existed, allowing dust to accumulate into growing bodies. Laboratory experiments on dust accretion, conducted in microgravity environments and with cometary analog materials, show that accretion is possible under the right conditions, but scaling these results to the coma of 3I Atlas requires assumptions about gas densities, dust properties, and timescales that are difficult to verify. One prediction of the accretion hypothesis is that the objects should show evidence of ongoing mass accumulation, not just expansion of existing material. If dust is continuously accreting onto the objects, their masses should increase over time and their spectra should evolve as fresh material is added to their surfaces. Monitoring brightness and spectroscopic changes over extended periods could test this prediction. Another prediction involves the spatial distribution. Accretion is most efficient in regions of high dust density, so if the hypothesis is correct, the objects should be located in or near the densest parts of the coma. Observations do show that the objects are relatively close to the nucleus compared to the extent of the dust tail, consistent with this expectation, though alternative explanations are possible. The analogy to protoplanetary disks also raises questions about the role of gravity. In disks around stars, gravity is the dominant force that gathers material and drives accretion. In the coma of a comet, gravity is weak, and other forces, radiation pressure, gas drag, electrostatics dominate. Can accretion proceed without significant gravitational binding? Some researchers argue that it can, through a process called electrostatic aggregation, where charged grains attract each other and stick through electrical forces rather than gravity. This mechanism has been proposed to explain dust aggregation in other environments, such as the rings of Saturn, and it could operate in cometary comae if conditions are right. Testing electrostatic aggregation requires in situ measurements of grain charges and local electric fields, data that are not available for 3I Atlas, but that future missions could provide. The accretion disk analog hypothesis, while speculative, illustrates how thinking across disciplinary boundaries, applying concepts from star and planet formation to cometary science, can generate new ideas and predictions. Whether the objects around 3I Atlas are actually accreting, or whether they formed through more conventional fragmentation and dispersal remains an open question. But exploring such analogies expands the range of possibilities and encourages observers to look for evidence that might otherwise be overlooked. The hypothesis also highlights a deeper theme: the universality of physical processes across different scales and environments, from planetary rings to protoplanetary disks to cometary comae, all governed by the same fundamental forces and potentially exhibiting similar emergent behaviours despite their vastly different contexts. Long-term stability analysis. What will happen to these objects over the coming years and decades? Long-term stability analysis uses orbital mechanics and evolutionary models to project their futures, assessing whether they will remain bound to the nucleus, escape into independent heliocentric orbits, or disintegrate entirely. The analysis begins with their current trajectories and velocities, which observations constrain to varying degrees of precision. Given these initial conditions and models of the forces acting on them, solar gravity, radiation pressure, gas drag, Yarkovsky effect numerical integrations can propagate the orbits forward in time, revealing possible outcomes. The results depend sensitively on parameters like mass, size, and reflectivity, all of which carry significant uncertainties. So the analysis produces a range of possible futures rather than a single definitive prediction. For objects with velocities well above escape velocity and favourable orientations relative to the Sun, the most likely outcome is eventual separation from 3I Atlas and entry into independent orbits around the Sunday. These objects would become small comets in their own right, though their limited volatile content and high dust-to-gas ratios would make them faint and difficult to detect. Over centuries, they would drift away from the original comet's trajectory, spreading out into a debris trail that marks 3I, Atlas's passage through the inner solar system. If Earth's orbit intersects this trail in the future, observers might detect meteor showers as dust grains from the objects burn up in the atmosphere, providing a visible legacy of the interstellar visitor. For objects with lower velocities, or those that experience stronger radiation pressure, the outcome could be re-impact with the nucleus, or gradual dispersal into the general coma. Re-impact would occur if the object's outward drift slows or reverses, bringing them back toward the nucleus on collision courses. Such impacts, even at low velocities, could trigger localized outbursts on the nucleus, ejecting fresh material and potentially creating new features. Dispersal, the gradual spreading of material into an ever larger, ever fainter cloud, is inevitable for objects that lack sufficient cohesion to remain intact. The timescale for dispersal depends on the object's internal strength. Strongly bound objects could survive for years or decades, while weak aggregates might disintegrate within months. Long-term stability also depends on external perturbations. Close encounters with planets, though unlikely given 3I, Atlas's hyperbolic orbit, could alter the object's trajectories significantly. Even distant encounters, where gravitational pulls are weak, can have cumulative effects over time, nudging objects onto different paths. Solar wind variations, particularly during periods of high solar activity, can change radiation pressure and drag forces, adding stochastic elements to the evolution that are difficult to predict. Modelling these effects requires Monte Carlo simulations, where many realizations with slightly different parameters are computed to build a statistical picture of likely outcomes. The long-term stability analysis also considers the possibility of further fragmentation. If the objects are internally weak, or if thermal stresses continue to build as they cool and heat with changing solar distance, secondary fragmentation could occur, breaking the objects into smaller pieces. This cascade fragmentation could produce a population of smaller objects that is currently below detection limits, but that might become visible as they spread out and catch sunlight at different angles. Evidence for cascade fragmentation would include sudden increases in dust production or the appearance of new discrete features in images taken months or years apart. One of the most valuable aspects of long-term stability analysis is that it generates testable predictions. By forecasting where the object should be at future dates, the analysis allows observers to plan follow-up observations that can confirm or refute the models. If objects appear where predicted, it validates the force models and parameter estimates. If they deviate significantly, it indicates that something is missing from the models, perhaps an unaccounted force, an incorrect mass estimate, or a fragmentation event that changed the dynamics. This iterative process, where models generate predictions, observations test them, and discrepancies drive model refinements, is the engine of scientific progress, turning the enigmatic objects around 3I, Atlas, into laboratories for testing our understanding of small body dynamics and evolution. Interstellar origin implications. The objects around 3I, Atlas, carry implications that extend far beyond their immediate physical properties. As fragments or companions of an interstellar comet, they provide a rare opportunity to study material from another stellar system, material that formed under conditions potentially different from those in our own solar system. The composition, structure, and behavior of these objects can reveal clues about the processes that shaped them in their birth environment, offering insights into planet formation, stellar evolution, and the diversity of planetary systems in the galaxy. The weak water content and enhanced carbon monoxide ratios, if primordial, rather than products of later processing, suggests that 3I Atlas formed in a region where the carbon monoxide to water ice ratio was higher than typical for solar system comets. This could occur in the outer reaches of a protoplanetary disk, beyond the snowline, but in regions where carbon monoxide remained in the gas phase during accretion, or in disks around stars with different chemical compositions than the Sunday. Alternatively, it could reflect formation in a molecular cloud fragment with unusual chemical enrichment, perhaps influenced by nearby massive stars or supernova ejecta. Each scenario makes different predictions about what other compositional anomalies should be present, and future detailed spectroscopy could test these predictions. The presence of organics, particularly if they are complex and diverse, points toward extensive chemical processing, either in the parent system or during the interstellar journey. Interstellar space is not a benign environment. Cosmic rays and ultraviolet photons from distant stars continually bombard any exposed surfaces, driving chemistry that does not occur in the relatively shielded environment of a planetary system. The organic inventory of the 3I Atlas objects, when fully characterized, can be compared with organics detected in meteorites, in other comets, and in samples from interstellar dust grains captured by spacecraft, building a picture of how organic chemistry varies across different environments. The interstellar origin also raises questions about ejection mechanisms. How did 3I Atlas escape from its parent system and achieve the high velocity needed to reach interstellar space? Gravitational interactions with giant planets can eject comets, but reaching the high velocities observed for interstellar objects typically requires close encounters with multiple planets or assistance from other dynamical processes, such as resonances or scattering by stellar companions in binary star systems. The specific trajectory and velocity of 3I Atlas, when traced back through the galaxy's gravitational field, might point toward a particular region of space or even a specific stellar system as its origin. Though such reconstructions are uncertain due to the long timescales involved and the complex dynamics of the galactic environment, the fact that 3I Atlas is only the third confirmed interstellar object detected, following Oumuamua and Borisov, highlights how rare these detections are and how much remains unknown about the population of interstellar wanderers. Statistical models, based on the detection rate and survey capabilities, suggest that interstellar objects pass through the inner solar system relatively frequently, perhaps tens per year, but most go undetected because they are too faint, or because they are not distinguished from solar system comets and asteroids in surveys. The unique features of 3I Atlas, its objects, its composition, its behavior, underscore the value of detailed follow-up observations on every detected interstellar object, as each one provides a unique snapshot of conditions elsewhere in the galaxy. The implications extend to astrobiology as well. If interstellar objects can carry organic molecules, and if they occasionally collide with planets, they could seed those planets with prebiotic chemistry, contributing to the emergence of life. This panspermia hypothesis, though speculative, gained support from the discovery that organics can survive the harsh conditions of interstellar space, and that objects like 3I Atlas can traverse vast distances while retaining chemically interesting materials. The objects around 3I Atlas, as fragments potentially carrying surface and near-surface material, might be particularly valuable targets for future sample return missions, offering direct access to interstellar material that could be analysed in terrestrial laboratories with instruments far more sophisticated than those deployable on spacecraft. Such missions remain distant prospects, but the scientific motivation is clear. and the discovery of objects like those around 3i, Atlas, makes the case for investing in the technologies and mission concepts needed to intercept and study interstellar visitors. Data integration framework. Making sense of the multitude of observations, models, and hypotheses surrounding the objects around 3i Atlas requires a systematic framework for integrating diverse data types and comparing them against theoretical predictions. Data integration is more than simply collecting measurements. It involves harmonizing data taken with different instruments at different times, under different conditions, and ensuring that comparisons are valid and that uncertainties are properly accounted for. The framework begins with a central database where all observations are archived in standardized formats, with metadata describing the observing conditions, instrument characteristics, and reduction procedures. This database serves as the foundation for all subsequent analysis, providing a single authoritative source that researchers worldwide can access and contribute to. Photometric data brightness measurements at different wavelengths and times are calibrated to a common system, typically tied to standard stars with precisely known magnitudes. This calibration removes instrumental effects and atmospheric extinction, ensuring that brightness comparisons across different observations are meaningful. Light curves are constructed by assembling photometric data in time sequence, revealing variability and allowing period searches. Spectroscopic data are wavelength calibrated and flux calibrated, transforming raw detector counts into physical units of flux per wavelength interval. Spectra from different instruments are often combined or stitched together to cover a broader wavelength range than any single instrument can provide, with careful attention to ensuring that overlapping regions match. Astrometric data positional measurements are reduced using astrometric software that accounts for telescope tracking, atmospheric refraction, and the motion of Earth. The resulting positions, typically with uncertainties of a few tenths of an arcsecond, are used to compute orbits and track the object's motion relative to the nucleus and to background stars. Combining astrometry from multiple epochs allows researchers to detect accelerations and to test whether the objects are following purely gravitational trajectories or whether non-gravitational forces are significant. The integration framework also includes tools for comparing observations with models. For example, thermal models predict temperatures and infrared fluxes as functions of size, albedo, and distance from the sunday. By running these models with different parameter values and comparing the predictions with observed infrared fluxes, researchers can constrain the parameters and identify ranges that are consistent with the data. Similarly, dust dynamics models predict how dust distributions evolve over time, and these predictions can be compared with observed dust envelopes, testing whether the models capture the physics correctly. Bayesian inference methods, which combine prior knowledge with new data to update probability distributions for model parameters, are increasingly used in this type of analysis, providing a rigorous statistical framework for parameter estimation and model comparison. Visualization tools play a crucial role in data integration, transforming tables of numbers into images, plots, and animations that human minds can interpret. Three-dimensional models showing the spatial arrangement of the nucleus, objects, and dust coma, with orbits traced over time, help researchers build intuition and identify patterns that might not be obvious from raw data. Interactive dashboards allow users to select different data subsets, apply different filters, and see results update in real time, facilitating exploratory analysis and hypothesis testing. The data integration framework is not static, but evolves as new data arrive and as analysis techniques improve. Software is regularly updated, new calibration procedures are implemented, and the database structure is refined to accommodate additional data types or to improve query efficiency. This ongoing development requires coordination among data providers, software developers, and end users, often facilitated through workshops and working group meetings where stakeholders come together to discuss needs, share expertise, and plan future directions. The ultimate goal of the framework is to enable any researcher, regardless of their location or institutional affiliation, to access the full body of data on 3I Atlas and its objects, to apply state-of-the-art analysis tools, and to contribute their findings back to the community. This open, collaborative approach accelerates discovery and ensures that the scientific return from observations is maximized, transforming scattered measurements into a coherent understanding of one of the most enigmatic phenomena in recent astronomical history. Today, as 3I, Atlas continues its journey past Mars, the mysterious objects that appeared around it remain a testament to how much we have yet to learn about visitors from beyond our solar system. Their growth, their composition, their very existence challenge established models and push the boundaries of cometary science into uncharted territory. The data accumulate, the observations continue, and with each new measurement, the picture becomes clearer yet more complex, revealing not simple answers, but deeper questions about the nature of interstellar matter, the processes that govern small body evolution, and the diversity of objects that populate the galaxy. The objects around 3I Atlas are not just astronomical curiosities, but windows into physics, operating at the intersection of multiple processes: thermal, mechanical, chemical, electromagnetic, each contributing to behaviours that emerge only when all factors are considered together, reminding us that the universe operates as an integrated whole, not as a collection of isolated phenomena that can be understood in isolation.